Hi fellow astronomers, my name is Eva Wen and my ZID is 5599592. In this video, I'll be analyzing orbital motion using a sun, planet, and planet-moon simulation, and I'll be focusing on questions about centers of mass, orbital velocity, and Kepler's third law. I'm also going to answer some questions first about the planet and moon simulation. So does the planet move as the moon orbits? The answer is yeah. It actually slightly moves or wobbles around its center of mass. Where are the centers of mass in each scenario from questions 1, 4, and 7? In all three scenarios, the center of mass was located near the center of the star. How is the planet-moon center of mass different to the sun-planet scenarios? In both scenarios, the center of mass is inside the massive body, but in the planet and moon scenario, the center of mass is relatively more closer to the surface. That's why we're able to see the planet bubble visibly. But why? Let's explain with a few steps. First of all, the Earth is made to orbit the Sun as the Sun exerts a gravitational force. Now, according to Newton's third law, objects have to exert equal but opposite forces. This means that the Earth has to also exert a force on the Sun in the opposite direction. Although the forces are equal in magnitude, their accelerations are actually inversely proportional to their masses according to Newton's second law. So even though the Sun and Earth pull on each other equally, the Earth is a lot lighter, so it accelerates a lot more while the Sun barely moves. In order to keep the system balanced, the point that they both orbit has to sit a lot closer to the heavier object, and since the Sun is so much more massive than Earth, the center of mass is quite close to the Sun's center, and as a result, the Sun appears almost stationary. Now, the Earth and the Moon have more comparable masses, so the Earth does a little wobble as the point of mass is more closer to Earth's surface. In many planet move scenarios, where the masses are even more comparable, the center of mass can even be outside of the massive body, and you can clearly see both objects orbiting a point in space between them, for example in some binary star analogues. What is the distance between each marking in AU? So AU stands for astronomical unit, and it's the distance from the Earth to the Sun. In this simulation, this is 2 grids, so therefore one grid must approximately be 0.5 AU. In questions 12, 13, and 14, we were asked to pick 4 different orbital distances and then adjust the velocity to make each orbit circular. I've recorded 4 different orbital periods from 0.5 AU up to 2 AU. Do these results follow Kepler's third law? Yes, Kepler's third law of planetary motion says that the orbital period is proportional to the semi-major axis of the orbit, or the orbital size. My results support that when orbital size increases, the orbital period should increase much faster. I translated my results into a graph, which resulted in a straight line. And my R squared means 99% of the variation in T squared is perfectly explained by R cubed, just as Kepler's third law predicts. Theory confirmed. Which planet in our solar system do you expect to have the fastest orbital velocity? I expect Mercury to have the fastest orbital velocity, and the slowest orbital velocity would be planet Neptune. The reason for this is because intuitively gravity gets stronger as an object gets closer to the Sun, pulling the planet inward more strongly. To stay in a stable orbit and not spiral into the Sun, a closer planet needs a larger centripetal acceleration. The way to achieve that is to move faster along the orbit. We can also work this out mathematically with 2 formulas. Number 1, the gravitational force exerted by the Sun, given by Newton's law of gravitation, and equate that to the centripetal force required to keep the planet in orbit. When we cancel out the planet's masses, rearrange for orbital velocity, we attain this equation. As g and m are constants, this shows that orbital radius directly affects orbital velocity for a given planet. Increasing the radius will decrease the orbital velocity required for a circular orbit. This is why inner planets like Mercury are going to move fastest. I learned that orbital motion is a mutual interaction between bodies, not just a one-sided motion, and I didn't know this before. It was very interesting to see how their center of masses change depending on their relative masses, and I also learned about how a planet's orbital velocity and period are strongly linked to their distance to the star, and how changing this velocity could mean totally different paths. Finally, I was able to see Kepler and Newton's laws in action. Thank you so much for watching my video, and I hope that was informative.